Power sources. As you know, every device in the world needs power. In electronic circuits, through the whole time of their operation, this energy is delivered from power sources. But before moving to the description of different types of sources, it is worth to mention a few parameters that characterize them. Basic parameters are rated current and rated voltage. Rated means that the source holds the value still, no matter what the parameters in the circuit are. So far, we used only ideal sources like voltage source or current source, but in the real world there is no such thing. The more load you put on the source, the more difficult it is to keep a certain value of current or voltage. In reality, there is also an internal resistance of the source. In case of voltage source, it is a serial connection of an ideal voltage source and a certain resistance. The more current is consumed by the system, the greater voltage drop will be present on this resistance. This resistance is composed mainly of resistance of electrode builders and resistance of electrolyte. If you want to know the value of the internal resistance of the source, you need an additional serial resistor in the circuit. If you know the value of this resistor and value of the voltage drop on it, you can simply calculate the current in the circuit. From the second Kirchhoff's law, you know that the sum of all voltages in the circuit must be equal to zero. Voltage drop on the internal resistance is equal to voltage of the source minus voltage drop on the load. From the Ohm's law, you also know that voltage drop on the internal resistance is equal to this resistance value times current in the circuit. Connecting these two equations let you calculate the internal resistance value. In case of the actual current source, it is a parallel connection of an ideal current source and a certain resistance. Because of that connection, a source is not able to maintain a current flow at a given value if you overload the voltage output. We often deal with portable voltage sources, such as batteries. An important parameter for them is their capacity expressed in ampere hours. A battery with 1 ampere hour capacity will work for 1 hour with 1 ampere before it discharges. The same battery may give you 2 amperes for 30 minutes or 100 milliamperes for 10 hours. Now we can move on to the most popular sources used in everyday life. The most common type of electricity source available in every home is the voltage coming from local low voltage power grid. This voltage comes from power plant. It has a sinusoidal waveform and it is described by two main parameters. The first one is effective voltage, which is equal to the constant voltage on the receiver, thanks to which the same amount of energy is released with alternating voltage. The second parameter is the frequency, which is responsible for the rate of change of voltage per second. Such a source generates alternating voltage, which changes its polarity. This means that for half a period, current flows in opposite direction. This is dangerous to human health and life, so devices powered this way must be serviced by trained and experienced people. We will not discuss it in our courses. Batteries are electrochemical voltage sources. They are represented by this symbol. This is a single cell, and depending on their number in the battery, the number of these segments may increase. Electrochemical voltage sources belong to the group of the DC voltage sources, which means that the voltage is constant over time. Such batteries can be found in remote devices where easy replacement of the power source is needed. It is worth to know that electrochemical voltage sources do not have constant voltage for the whole time of their operation. When the battery is fully charged, the voltage is slightly higher than nominal one. During operation, the voltage slowly decreases until the battery is discharged. If you discharge it further, After this sudden voltage drop, cells are damaged and the battery becomes useless. Accumulators. Compared to accumulators, batteries have one major drawback: they are disposable. Accumulators can be recharged multiple times. However, you have to remember not to discharge them below the limit we discussed previously. There are several types of accumulators. The first one are nickel-cadmium and nickel metal hydride. They have relatively low voltage, around 1.2 volts, and relatively low capacity. These batteries have also a so-called memory effect. Depending on charge and discharge cycles, they lose capacity over time. The next type are lead-acid and gel batteries. They have voltage of 12 volts and large capacity, up to around 20 ampere hours. They are used mostly in cars to start the engine or in UPS systems to maintain voltage when the primary power supply is out of order. The main disadvantage is their large mass. Lithium-ion and lithium polymer batteries can also give very high current thanks to the low resistance of around several dozen milliohms. Their disadvantage is considerable susceptibility to temperature shocks and mechanical injuries. Unsealed cells release a lot of toxic gases due to the high reactivity of lithium. They have several important parameters that characterize them. The first one is maximum discharge current and the second one is maximum charging current. Both are expressed in capacity multiplication with letter C. If you have 500 mAh 20C battery, this means that the maximum discharge current is 10 amperes. Maximum charging current should not be greater than 1C in order to lengthen the battery life. The next parameter is the battery voltage defined with letter S, meaning a serial connection of subsequent cells. For instance, 6S means that you have 6 3.7 volt cells in a serial connection, which gives you 22.2 volts. These batteries may also be connected in parallel to increase the overall capacity or current efficiency. This type of connection is defined with letter P. Let us consider two examples: 4000 mAh 15C6S1P battery and 2500 mAh 50C4S2P battery. The first one is 4 ampere hours battery with maximum discharge current of 60 amperes and nominal voltage of 22.2 volts. There are 6 serial cells. The second one is 2.5 ampere hours battery with maximum discharge current of 125 amperes and nominal voltage of 14.8 volts. There are 2 parallel rows, 4 cells each. The last important power source are power supplies. These devices are connected to the local low voltage power grid. Their task is to generate at the output DC voltage as stable as possible. They may have different output voltages, different current capacities, sizes, protection ratings, and so on. Output voltages might also be regulated, especially in laboratory power supplies. Power supplies are frequently used in personal computers, servers, chargers, or RTV devices. Most of power supplies have a so-called galvanic separation. This solution allows to transfer energy and information in forms other than electric current, such as optically with optocouplers or magnetically with transformers. This solution prevents from electrocution from the electricity network because potentials on primary side are not related to the potentials on secondary side. Power supplies can be divided into 2 groups in terms of internal design. There are linear power supplies and switched mode power supplies. In both of them, you can separate several main function blocks. In linear power supplies, the first one is transformer, which transforms network voltage to much lower voltage and acts as galvanic separation. The next one is rectifier, which changes current from alternating to direct. Third block is ripple filter, consisting of large capacity capacitors, which store energy in order to maintain voltage and low ripple level. If the power supply is stabilized, it also has a voltage stabilizer to reduce load and temperature influence on the voltage level. These power supplies are relatively cheap and simple, but they are also heavy and inefficient. The other type are switched mode power supplies, SMPS in short. The principle of operation is similar to that of linear power supplies, however, the system is more complex. Frequency of voltage changes in the power grid is relatively slow, around several dozen times per second. This forces the use of large cores in transformers. Transformers in SMPS are much smaller and they work at frequencies of around several dozen kHz. At the input of SMPS, there is a rectifier with ripple filter. The next stage is a transformer connected to transistors which act as keys with frequencies of many kHz. On the secondary side, there is another rectifier and filter which transform voltage from alternating to direct. The last important block is a feedback circuit. It passes information about the output voltage to the input of the generator for correction purposes.
Now we'll talk about the most important device in electronics, a universal meter known as multimeter. This device is able to measure many electrical quantities, sometimes also temperature. We can divide them into stationary and portable ones. The latter are much more popular. Each of them should measure voltage, current and resistance, but often also they have the ability to measure the capacity of capacitors, test diodes and circuit continuity. In this training, we will focus on the portable version. Before we discuss the most important features of the multimeters, we have to know how to incorporate them safely. Let us start with the voltage meter. The voltmeter, as the name suggests, measures voltage in volts. As we remember, the voltage occurs between 2 points, so the voltmeter is always plugged in a parallel to the tested system or element. The voltmeter section in the measured meter should have the highest possible internal resistance, so large that the parallel connection of the voltmeter's resistance to the systems does not cause a noticeable increase in the power consumption. This resistance reaches 10 mega ohms and more, even 100 mega ohms. If you turn the probes on the opposite side, you will see a minus sign with direct current at the same value with the alternating one. However, when we make a mistake and turn on the voltmeter in a series, it is possible that the system will not work at all, because such a large resistance will flow so low that the system may not be turned on. Always take special care of the probes to be connected to the COM terminals and the voltage measurements to V. When measuring the voltage, if we made a mistake and the probe would be in a terminal for current measurement, we could damage the system by shorting. The ammeter measures the current flowing through it. From the Kirchhoff's first law, we know that it should be plugged in series in our circuit. So before plugging our ammeter, we have to disconnect the circle. The meter should have the lowest possible resistance to cause the lowest possible voltage drop. Analogously to switching on the probes, which we plug into the COM and A or MA terminal, on the opposite side we will see a minus sign with direct current and the same value with the alternating one. Previously, we told you about how important is to connect properly the ammeters and to know which terminals we are using. Connecting ammeter in a parallel may result in a short circuit and a very big current flowing through it that can damage our system. The ohm meter or resistance meter is connected in parallel to the elements whose resistance is to be checked. It should be remembered that for proper checking, these elements should be desoldered. Mounted in a system are connected with others and the result measurement can be falsified, with the result resistance seen from between the probes. We measure capacitors with the capacitance meter. We connect it to the parallel to these elements, remembering the most important thing. Each capacitor must be unloaded before measurement. The input circuits are very sensitive and the capacitor desoldered, for example from a power supply or flash, can have hundreds of volts on it, which can immediately damage our meter. The diode and the continuity tester is used to check whether after connecting to a given semiconductor element, a voltage drop is presented on them. It is worth noting that many meters use voltage sources in their construction with value approximately 1–2 volts, some even 4 volts. Thanks to the increased voltage, we can check the LEDs, but this has one disadvantage. Voltage with such values may cause the inclusion of some elements and the flow of currents, which may affect the state of the tested element. Reading may be distorted. The circuit continuity tester is usually located in the same place as the diode tester. Its operation is based on the fact that if the meter detects a resistance below usually 75 ohms, it will start to squeak through the piezoelectric transducer. It is useful for checking short circuits or connections on complicated PCBs. Sometimes we may not be aware that a very thin path has been interrupted and we cannot observe it with naked eye. It is enough to apply one probe to the place on the element and the other on the place where the path is to go. We will find out then through the sound whether there is a connection or not. We divide the multimeters into analog and digital ones. The former are less and less used due to the lower accuracy and sensitivity to shocks and magnetic field. In digital, we do not have a scale with a pointer, but the LCD display with the right number of digits. It also contains a place for batteries or accumulator, a range selection, and connection terminals. In the vicinity of the dial, we have individual ranges of measured values. It is worth noting that the multimeters can measure the values of voltage and currents, not only constant but also sinusoidal variables. Better class meters measure the effective value of true RMS. When, for example, we measure voltages of 1–2 volts, we can set the appropriate nearest range. However, when the voltage increases, the display will show that we have exceeded it and should be set to the higher. One could ask a question why we do not use only the highest range. Each meter has its measurement error determined as a percentage of the given range, plus minus error of the last digit. So if we were measuring the voltage of 1 volt on the 100 volts range, it might turn out that the error could be 0.2%, 200 millivolts, plus minus 2 on the last digit, and when we could see a value, for example 1.4 volts. It is worth adding that the lowest range, often 200 millivolts, 400 millivolts, etc., is the most accurate and the least protected, so be careful when you want to measure very small and high voltages. The second meter automatically selects the range. This function is called auto range, so we do not have to wonder if we have chosen it optimally to get the most accurate value possible. It is also very important that when measuring the alternating voltage in an ordinary meter, it will have high accuracy only for voltage with sinusoidal voltage and the specific frequencies, hundreds of hertz. If we need to examine signals of a different shape or higher frequencies, it will be used to measure the RMS value, true RMS. A multimeter is a very basic and useful device for measuring and diagnosing systems. But before we start to work with it, we should know what size we are measuring, to what terminals should be probes connected, and how to turn on the meter. The electronic engineers, when constructing their systems, often have to examine them in order to check the correctness of operation, parameters, work safety. Sometimes we build them for a later work with an external power supply, and we need to know their power consumption. One of the most important workshop equipment is a workshop or laboratory power supply. It is a type of power supply with smooth voltage and current regulation. It has a built-in voltmeter, ampermeter, and should have various types of protection: overload, overvoltage, thermal. In this part, we'll focus on its use. Such power supplies should have voltage regulation, preferably from 0 volts, implemented in a form of a multi-turn potentiometer or potentiometer for roughing, coarse, and fine adjustment, fine, or a rotatory encoder or other digital regulation, for example, taping value using the keypad. The current adjustments should look the same. Let us consider the situation that we are required the supply of several amperes to our system. It may turn out that through the voltage drop on the wires, the tested device will not work properly or will not check its most important parameters. The built-in voltmeter measures the voltage at the terminals and not at the ends of the wires. Some power supplies have the option of connecting so-called 4-wire. The 2 internal terminals are responsible for providing the current, and the 2 external terminals are connected to the ends of the wires in such a way that the current flowing through them is negligible. Thanks to such solution, there is voltage on external terminals, such as in the tested device. We can also meet a multi-channel power supplies. They can expose 2 different or the same voltages and currents. Some have the option of channel bridging. This means that we can connect the channels in series in order to increase the voltage or create symmetrical voltages, or in parallel when one channel has too low current efficiency. It should be noted that the channels in the power supplies should be completely separated from each other. Setting the voltage to a value of, for example, 5 volts, we expect that it will be constant. The system then acts as a voltage stabilizer, constant voltage, CV. When we set the current to, for example, 100 milliamperes, until we exceed this value, the voltage will not decrease. After exceeding this current, the voltage will be corrected to maintain the current flowing 100 milliamperes. The system then acts as a stabilizer current, constant current, CC. We know that no matter what we connect to the power supply with such settings, will not receive more than 5 volts and 100 milliamperes. Such solution in the power supplies give us 2 possibilities. Let us consider a situation where our system should be powered from 15 volts. We do not know if it's operational. If we did not set a limit and a short circuit would occur, for example, in the power section of our system, we would allow a significant current to flow through it, which could damage function components or paths on the PCB. However, if we anticipate that the system should take no more than 200 milliamperes, then no more electricity will be flow through the system at the moment of short circuit. We can observe such a state by the fact that the output voltage has dropped, or by changing the backlight of the controls from CV to CC. The second option is to test circuits or components that require proper power supply from a power source. An example can be LED diodes. Many of them, about 90%, achieve their maximum safe brightness at a current of approximately 20 milliamperes. Depending on what type it is a diode, what is the color, the voltage drop will be different. For the infrared diode, 1.2 volts, for the red diode, 1.4 volts, and for the white diodes, it is around 3.2 volts. Sometimes we do not know, and in this case we can set the power supply for 10 volts and voltage and 20 milliamperes current limit. However, already at 2 volts, the diode would start to take over 20 milliamperes, so the power supply will switch to the current stabilization mode and it will work in its safe range. An oscilloscope is a measuring device representing voltage in a time domain. We can call it the eye of an electronic engineer. The meter was a device that showed us electrical quantities in a form of a numerical value, with or without a sign. The oscilloscope shows us the voltage at a given moment in such a way that it draws a graph from the left side of the screen to the right. It is so-called plots that, depending on the selected range, represented voltage or time. Their inputs have a high resistance, in order of mega ohms. Therefore, they can do overload circuits, and voltage probes should be connected in a parallel like in voltmeter. These are the most common ones, but sometimes we can see the current probes which are switched in a series. Oscilloscopes usually consist of 2 or 4 channels. Each channel has the option of choosing a voltage range per plot. For example, if we set the range to 1 volts per plot, the course that changes between 3.5 plots will have 3.5 voltage changes. The second function is to adjust the position on a screen. It is helpful when you want to observe the waveforms on many channels at the same time, or when it turns out that the input voltage is so high or so low that the image is currently being drawn outside the screen area. We should also be able to choose the type of input voltage. There are usually 3. The first is GND. The input is switched directly to the zero oscilloscope, so we can then calibrate the position of the waveform on the screen. The second is DC. Then the voltage from the input is drawn on the display without transformation, of course taking into account the selected range. The third type is AC. Here the capacitor cuts the fixed signal components in series. Let us consider the situation where we measure the voltage of 20 volts and we want to investigate the disturbance. It is easy to notice that often these have much lower voltage than a constant voltage, for example here 20 volts. So we can take out this tension, leaving only this curve that changes quickly. Oscilloscope can often only display a given channel, selected by us, or can also perform mathematical and logical operations, like add or subtract voltages from individual channels. The next section is the time-based adjustment sections. Depending on whether the signal changes quickly or slowly, we want to observe it as accurately as possible. Here the situation is analogous to that with the voltage ranges. If we observe that our course repeats its shapes periodically every 10 micros of seconds, because we choose a range of 2 microseconds for a plot and one period took 5, it means that the voltage changes with the frequency 100 kHz. One of the most important functions in oscilloscope is setting the correct operation of triggering system. The system is used to draw waveforms from the beginning, left side of the screen, at appropriate time moments. If you were to draw the waveform continuously without triggering, they would be illegible and unstable. To set the trigger module correctly, first select the signal's source. These can be input channels, external dedicated input. We use only channel 1, so we set it as our source. The last in the order is the trigger threshold, level. This is the voltage value at which the system will start to draw the waveform from the left to the right of the screen. When you observe periodic waveforms from 2 or more channels at the same time, all of them should be stable when the triggering is set correctly. If we are dealing with non-periodic waveforms, then the picture will not be stable. Digital oscilloscopes have a built-in memory, and thanks to it they can test non-periodic, impulsive and other random events by means of triggering. When we set the triggering level appropriately and turn on the signal mode, the oscilloscope will snap the image until the user decides that he has analyzed the waveform. These were the most important measuring systems and power supplies. We have learned about the power supplies, DC voltage sources and other voltage sources. We have also learned about how to use measuring systems such as oscilloscopes or multimeters. In next episode, we'll focus on building and constructing our own electronic circuits.